Ranjan Kumar Kalindi, and from today onwards we are going to start a electronics engineering special class. This class for those who are preparing for government exam which are related to electronics discipline. Either you are from electronics branch, electronics telecommunication, electronics and communication, or electronics or instrumentation, and whatever branch is there where you have digital electronics, you can watch this one. And this is for this class is helpful for all kind of exam. There this subject is there. Okay, in this one class we are going to cover full concept and all things as a short note. Means I will discuss all the concept here which will helpful for your exam. Okay, so I will start. For PDF and more updates, you can join our Telegram channel. This is my Telegram channel name, Hardwork Limited. You can join here directly, or just go to description box. There you will get a link. Just join this one. Here you will get PDF notes and class update. Everything I will update in this channel. Okay. So basically, if we talk about digital electronics, in digital electronics, there are this topic we have in a digital electronics. From their questions are coming in a exam, like number system and codes, logic gates, logic simplification technique, logic circuit, counter, shift register, and data converter. Okay, so we'll discuss one by one. First, we'll start with our introduction. Like if we talk about digital electronics, digital electronics is what? Digital electronics is nothing but a it will deal with a digital signal and system that operate using a binary logic, zeros and ones. Digital signal means what? Digital signal, it is dealing with only digital signal. If we talk about a message or information, generally it will go in the form of signal. Okay, and we have two kind of, if we see, we have generally we have two kind of signal. First one is your analog, okay, analog signal, and another one is your digital signal. Okay, if we talk about analog signal, in analog signal it have different amplitude. Like if you see the graph of analog signal, then it having different amplitude in each time period. Okay, you can check, you can see here we have different amplitude with time interval. Okay, so like here you can consider this is 1, this is 2, this is 3. So we have different amplitude. Here also this is -1, then this one is -2. So analog signal have different amplitude. And if you see digital digital signal, then digital signal only deal with two amplitude. Okay, only two amplitude is there in digital electronics. Digital signal. Okay, so like if it is if it is 1, then it will be -1. So only two signal and two amplitude will be there in a digital signal. Okay, so we are dealing in a digital signal, we are dealing with only two amplitude. Okay, that two amplitude we are telling in a digital signal as a high and low. Okay, like this one we are considering as a high signal, and this one we are considering as a low, or you can say 1 and 0. Okay, 1 and 0. Some other name is also there, like true false, then mark space. Okay, so like that we are dealing only with a two signal. So generally in a digital signal we are following 1 and 0. For high it is 1, for positive it is 1, and for negative it will be 0. Okay, so based on that we have first topic is a number system and code. Okay, number system is what? Number system is nothing but, number system is the way of representing of number. Okay, the way of representing a number is called number system, and we have standard unit of number system, that is we call base or radix, that will be represented by r. Okay, so this is what, this is number system. Now number system, in the number system we have in a digital signal we have four kind of standard, four type of number system we have in a digital electronics. Okay, so that will be your first one is your binary, then we have octal. Okay, then we have decimal, and we have hexadecimal. Okay, this number system we have four number system. Okay, and if we talk about base, or we can say radix. Okay, base or radix means what? Base and radix means it will be represented by like this. Okay, binary means it will be 2. Okay, octal means it will be 8, and decimal means it will be 10. Okay, and hexadecimal means what? Hexadecimal means it will be 16. Okay, so like this radix or base we are representing for a different number system. Now if we talk about maximum digit, okay, so if we talk about maximum digit, so in this maximum digit is what? Maximum digit is r minus 1. That is your r means what? R means 2. 2 minus 1 is 2. Same here, r minus 1, maximum digit formula is r minus 1. So r minus 1, 8 minus 1 means 7. In a octal maximum digit will be 7. For decimal it will be r minus 1, that will be your 9. 10 minus 1 is 9. So in decimal maximum digit is 9, and in the hexadecimal it will be your r minus 1. Okay, r minus 1, that will be your 15, or we are representing this as a f. Okay, now if we talk about digit, okay, what kind of digit is there in all the number system? For binary it will be it having maximum digit 1, means it will be 0 or 1. Okay, then octal it will be 7, means it will go 0 to 7, 0 1 2 3 4, like that it will go till 7. Then for decimal it will be 0 to 9. Okay, and for hexadecimal it will go first 0 to 9, and after that from 10 to f, 10 to 15 we are writing as a to f. Okay, uh, till 10 it will be 0 to 9, it will represented by 0 to 9, and after 10 to 15 it will be like, if we have 10, 11, 12, 13, 14 and 15, then 10 will be a, this will be b, this will be c, this will be d, this will be e, and this will be your f. So number system is the representation of number system in a digital electronics is like this. We have four number system, that we have this table. Just remember this table, it will be helpful for your exam. Okay, now if we see number system conversation, we have different type of number system. We have four kind of different number system. Now how we will convert from, like if we have binary, then how we will change from binary to decimal, decimal to binary, binary to octal, octal to decimal, or binary to hexadecimal, like that conversion is there. So for this for that some rule and regulation is there that we need to follow. Like for number system, if we talk about number system conversion, then first the first system is what? The first rule is, first like if you want to convert from decimal to suppose you want to convert from decimal to other systems. Okay, you have given decimal number, and you have to change this in another form. Another form means anything, like first if we take example of, suppose we have 126. Okay, 126. If we have decimal number 126 and we need to convert this thing in a binary form. Binary means it will come 0 and 1 only. Okay. So for decimal to other system, what we will do? We will from decimal to other. If you want to convert from decimal to other system, you need to follow the division method. Okay, division method means we have 126 here. If you divide this 126 from like binary, this base is 2 is there, so we need to divide with 2. So from 2, if you divide, you need to write the remainder this side, this is what 6 and 3, 63 times 63 into 2 is 126. So it will there will be no remainder, means 0 remainder is there. Okay, now if you divide 2 to 63, then it will come what 3 and 1 31, and here you will get 1 remainder. Okay, now if you divide 31 to 2, then it will come how much? It will come your means 15 into 2 is 30 and 1 remainder. Okay, now if you divide with 2, then 7 into 2 is 14, so 1 remainder again. Now if you divide with 2 again, then it will come how much? It will 3 into 2 is 6, so 3 and 1 remainder. Now if you divide by 2 again, then it will come 2 2 1 ja 2, so 1 here and 1 you will get remainder. So you need to divide till last, like after that you can't divide from 2, so till then you need to do the division. Okay, and after that you need to write this number like this, you need to represent. From here you need to start, this will be 1, and again here 1 1 1 1 1 2 3 4 5 6 1 2 3 4 5 6, and this one is 0. So this is the representation of decimal number of 126 in a binary form. Okay, so this is the representation of what decimal to binary. Okay, now if they will ask, like this is binary to decimal, suppose they will ask same thing like 126 we have, 126 we have as a decimal, and we need to convert this one in a octal form. Okay, now if you want to if you need to convert this thing in a octal form, then same you need to do division method. Here you have base is a 8, so here what you need to do, here you need to just do is like 126 you need to divide again. Now here base is 8, so you need to do the division with 8. Okay, so if you divide this one, just divide 15 times, so you will get remainder 6 here. Now again if you divide with 8, then you will get 1 here, and remainder you will get 7. So again you need to write like this. So 176 is a octal form of 126 decimal. Okay, now suppose same thing, if they will ask, like if they will ask you to convert same thing in a what, this is binary octal. Now another one is 126 decimal if you have given, and you need to convert this thing in a hexadecimal. Okay, now hexadecimal means base 16. So base 16 means what? You need to do the same division method. 126, now you need to divide with 16. So from 7 time it will go, and you will get 14 remainder here. Okay, and now you need to write like this. Okay, means you need to represent from like this. So 7 and 14. 14, how we are representing 14 here? 14 means what? 14 means E. So this is the hexadecimal representation of 126. Okay, so if anything will come from decimal to binary, decimal to octal, decimal to hexadecimal, you need to convert like this, you need to follow this method. Okay, sometime, okay, this is question, this is another question, and this is another question. Okay, sometime they will ask question like, suppose if you have 126.25, it is given in decimal. Sometime point wala question is also coming, like 126.25, if 25 is there, then you need to convert same thing in a binary form. Then how you will convert that? So if you will get any kind of this dot wala thing, means after decimal they will give, and from decimal you need to convert some other system. So same thing you need to do, like before this decimal left hand side, that is 126 is there. For 126 decimal number you need to follow same division method. Okay, same division method you need to follow, and here you will get how much, this one. If you follow this one you will get 1 1 1 1 1 and 1 and 0. This one you will get for 126. Now for 25. Okay, now for 25, 25 means what? 0.25. Now from the right hand side, for right hand side, what you need to do? If it is 2 is there, you need to do multiplication with 2. If binary is there, you need to do with multiply with 2. Okay, so what? 0.25 into 2 is what? 0.50. Okay, and again you need to take this decimal part only, means that right hand side. So 0.50 into again 2 is what? Is 1.00. Again you need to means you have to do this multiplication till after this decimal you will get 00, means 00. If 00 will come after decimal, then no need to do further multiplication. Okay, and here you need to represent like this. From decimal, before decimal it is 0 is there, so 0. Before decimal 1 is there, so it will be 1. Okay, so here it will come 0.25 means 0.25 means what? It will be your 0.01. Okay, you need to write like this, like this you need to write the number. So first one is 0 and another one is 1. Now the representation of 126.25 decimal form in a binary, that will be, you need to write this one full 1111110, then dot 01. This is the binary representation of 126.25. Okay, if you get here octal number, then you need to multiply with 8. If you get hexadecimal, then you need to multiply with hexadecimal, means that is 16. Okay, now just a second. Okay, now the first one is your decimal to other. Now the second one is, if you get other system to decimal. Okay, now you know how to convert from decimal to other system. Now if you get other system to decimal means what? Suppose like we have done 126, so 126 binary number is what? 11111 and 0. Okay, this is what is the, they will ask, this is the binary representation. Now what is the decimal number of this? You need to convert like this from by other system to decimal. So how you will resolve? For decimal to other you need to do division method, and from for other to decimal you need to do multiplication method. Multiplication method of what? If you will get any kind of number, you need to write like this. Okay, like this you need to write. This one is the position of 2 to the power 0. This is the position of 2 to the power 1. This is 2 to the power 2. This is 2 to the power 3. This is 2 to the power 4. This is 2 to the power 5. And this will be 2 to the power 6. Okay, now what you need to do, where you are getting, means 2 to the power 6. So from here you need to write like 2 to the power 6 into, here 1 is there, so you need to multiply with 1. Again you need to plus 2 to the power 5, you have 1 there, so 1. Then 2 to the power 4 into 2 to the power 4, you have 1, so 1 you need to multiply. Then 2 to the power 3, 2 to the power 3 you have 1, so 1 you need to multiply. Again 2 to the power 2 you have 1, so 1 you need to multiply. Again 2 to the power 1 you have 1, so again 1 you need to multiply. Then plus, then again 2 to the power 0, 2 to the power 0 into, here you have 0, so you need to put multiply with 0. Now you need to do simply calculate. Okay, 2 to the power 6 means what? This is 64. 2 to the power 5 into 1 means what? 32. And 2 to the power 4 means 16. 2 to the power 3 into 1 means 8. 2 to the power 2 into 1 means 4. And 2 to the power 1 is 2. Then 2 to the power 0. Anything into anything multiply anything power of 0 is 1, and 1 into 0 is 0. Okay, now you need to do the simply addition of this. 64 plus 32 plus 16 plus 8 plus 4 plus 2 is equal to what? Is equal to 126 decimal. That we have done before, decimal to binary. Now we have checked also from binary to decimal how we are getting 126 only from this method. Okay, and now if we will see the further next one wala. So next one, as we have seen about what? Octal number. Octal is 176. Now we will check 176. 176 we have octal, and now they have asked to convert this thing in a decimal form. Okay, so 176, how we will do? Again same process. Like this you need to write. Here 8 is there, so it will be 8 to the power 0. Here 8 to the power 1, and this one here 8 to the power 2. Now you need to write 8 to the power 2 into, here 1 is there, so 1, then plus 8 to the power 1 into, in 8 to the power 1 you have 7, so 7 you need to multiply. Then plus you have 8 to the power 0, 8 to the power 0 into, this one is your 6, so 6 you need to multiply. Now again you need to do the means what? Mathematics. So 8 to the power 2 into 1 is what? 64. This one is 56, and this one is 8 to the power 0 means 1. 1 into 6 what? 6. Okay, now if you do 64 plus 56 plus 6 is what? Is 126. Okay, 126 in a decimal form. So from octal to decimal we will get like this. Now again we will check another one, that is your what? Hexadecimal. Hexadecimal is 7e. Okay, if suppose they have given 7e as a hexadecimal, okay, and you need to convert this thing in a binary form, decimal form. So same process, like this you need to write. Here 16 is there, so 16 power 0 and 16 power 1. Now 16 power 1 into 7 plus 16 power 0 into e means what? E means 14. Now this one will be 16 into 7, 112, and 16 to the power 0 is 1, 1 into 14 is 40. Now if you calculate this thing, you will get 126 decimal. So like this, from decimal to other and other to decimal, you need to do the conversion. Okay, now one more thing we will check, that decimal wala part. In decimal we have like if you have given another question, we'll consider 1111161 na 1111161 and 0. This is 126. Then 0.1 that we have get in a previous, this one 1111 0.01. So we'll check this binary number, how it will convert now to decimal number. Now what you need to do for this? So for this same thing, for this part you need to, means from decimal to this side, you need to follow same method. Okay, as we have seen here, like 2 to the power 0, 2 to the power 1, you need to multiply till 2 to the power 6, and you need to calculate that one. So same method you need to follow for this calculation. So this will, we will get 126 anyhow if we are going to do that one. And from point, means after decimal, what you need to do after decimal, you need to go like this. Okay, like this you need to go, and from here first position is your 2 to the power minus 1, and the next one is 2 to the power minus 2. Like this you need to go. If you have more number, then you have to put 2 to the power minus 3, 2 to the power minus 4. Like this you need to go. Okay, So now from here, for 2 to the power minus 1, 2 to the power minus 1 into 0, then plus 2 to the power minus 2 into 1. Like this you need to do the calculation. 2 to the power minus 1 means what? We can write this one 1 by 2 into 0, and we can write this one 1 by 2 to the power 2 into 1. So this will be your 0 plus this will be your 1 by 4. So it will be your 0 plus 0.25, that will be your 0.25. Now you need to write both together. So it will be your 126.0, sorry, 126.25. You will get this decimal number. Okay. So like this you need to do the conversion of decimal to other and other to decimal. Okay. Now some other system is there. Now till now we have known, like till now we got how to change decimal to other system and other to decimal. Suppose now decimal thing we know. Now if they will ask another thing, the third one is your, if they will ask octal to binary, octal to binary. Okay. Now we need to convert octal number to a binary number. Okay. For that we will take one, like if we consider 125 here, 125 we are given as a octal. Now we need to convert this thing in a binary form. So binary, for binary conversion, what you need to do, you need to remember one table. That table you need to remember. For binary we are writing like this: 0 0 0 1 1 0 1 1. Okay, this is what this will represent 0, this will represent 1, this will represent 2, and this will represent 3. Okay, and if we put more 0 0 0, okay, 4 0, like this, what we need to do, we need to put more 4 1 here. Okay, and same thing, this same thing, like we need to write here 0 0 0 1 1 0 1 1. Okay, so from here we can now go for another, means next, like this will be representation of 4, this will be representation of 5, this will be representation of 6, and this will be representation of 7. Now if we put more 0 0 here, okay, if we put more 0 0 here, and for, like you can see here, 8 times we have put here 0. Now you need to put 4 times 1 also, 1 1, sorry, 8 times 1 1 1 1 1 1 1 and 1. So 1 2 3 4 5 6 7 8, 8 times 1 you need to put, as we have given 8 times 0 here. Now same thing, from here to this all part you need to write same. So it will be 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. Like this you need to remember this table. So this is the representation of 8, this is the representation of 9, this is 10, this is 11, this is 12, this is 13, this is 14, and this is 15. So from 10 we are writing as A, B, C, D, E and F. We will represent like that after 10. Okay, so now we have 125 and we have octal number. Octal number means what? 2 to the power 3 is equal to what? 8. So here you are getting 3. 3 means you need to represent, we need to find the binary. So 2 to the power 3. 2 to the power 3, 3 digit we have to represent for each character. Suppose we have 125. So what we will do, for 5 you need to write 3 digit binary, for 2 we need to write 3 digit binary, and for 1 we need to write 3 digit binary. So for 5, 5 is here, so 3 digit representation is 101, and for 2, 3 digit is 010, so 010, and for 1 it is 001, so this is your 001. So this is the representation of binary number from binary number of 125. So 125 octal is represented by binary as a 001010101. This is the representation of binary number. Okay. Binary to octal, same if they will ask from binary to octal. Okay. If first question will come your what octal to binary. Now if they will ask from binary to octal, how you will convert from binary to octal. So for binary to octal conversion, same question if they will give like or you can consider anything, or you can consider this one only 001010101. This is the binary representation. Now you need to convert this thing in a octal form. So from left side, sorry, you need to go from right to left. Okay, right to left you need to go and you need to make a pair of 3. So this 3 you need to make a pair, after this 3, and after that this 3. So this is what, this is 101. 101 is what, 101 is 5. 010 010 is what, 2. So this is your 2. Then 001 001 is what, 1. So this is your 1. So this is 125 octal representation. Okay, like this you need to do. Now same thing if you got another one is what, octal to binary. Okay, now if you got question like hexadecimal, okay, hexadecimal to binary. If they will give question about hexadecimal, suppose 2A5 you have given 16 means hexadecimal. Now you need to convert this thing in a octal form. So same thing you have to do from like this, like 2A and 5 you need to represent 16 is there. 16 means 16 means what, 2 to the power 4 equal to 16. So you need to make a, means you need to represent by a 4 digit of a binary form. So 4 5 representation of 4 digit is what, 0 1 0 1. A means what, 10 means this one. So 1 0 1 0, and 2 is what, 2 is what, 2 is your 0 0 1 0. So this is the representation of hexadecimal to binary. Okay, same method if they will ask for binary to hexadecimal, for binary to hexadecimal. So binary to hexadecimal, same thing. Suppose they have given 0 0 1 0 1 0 1 0 0 1 0 1. If they will give binary, you need to convert same in a hexadecimal. So same thing, whatever we have did in octal, we have made 3 pair. So here you need to make a 4 pair. So like this you need to make 4 pair. Okay, and same thing, 0 1 0 1 is what, 5. 1010 is 10, 10 is A, and 00100 is 2. So this is what, this is your hexadecimal representation. Okay, so like this you need to do. Okay, now you know how to convert decimal to other to decimal, octal to binary, binary to octal, hexa to binary, and binary to hexadecimal. Okay, now one thing is, now we have still one thing, that is your what, octal to hexadecimal. Okay, octal to hexadecimal. Now we have left with octal to hexadecimal. Suppose we have 125 as a octal, and we need to convert this thing in a hexadecimal. So what you need to do, you need to make, first you need to convert this thing in a binary form. So for binary form, what we will do, we will make 3 pair. 3 pair is what, it will be 101, it will be your 010, and it will be your 001. Okay, now for hexadecimal representation, what we need to do, this we got binary form. Now to represent in a hexadecimal, we need to make a 4 pair. So here you need to make 4 pair like this, here you need to make 4 pair like this, and if you have, like you are not able to make a 4 pair, then you need to add 0 0 left hand side. Okay, so now it will become 4 pair. Now you have to represent like this. This 0 0 0 is what? 0. Then 0 1 0 1 is what? 5. Then 0 1 0 1 is what? 5. So this is the representation of hexadecimal. So 055 octal to 125 of octal is what? 055 hexadecimal. Same thing if they will ask from hexa to octal. If they will ask from hexa to octal, then uh, like if you see, if we make same thing, like if we consider same thing also, what? 0 0 5 5, okay, 0 5 5. If we do same thing, 0 5 5 0 5 5 we have in a hexadecimal, we need to convert this thing in a octal form. Okay, so 0 5 5, same thing, you have to make 4 bit, you need to represent all this thing. So 4 bit is what? 0 1 0 1 0 1 0 1, and this one is 0 0 0 0. Now you need to make 3 pair, so this will be your 3, this will be your 3, and this will be your 3 till here. Okay, so it will be what? This 101 is 5, and 101 is 5, 010 is 2, and 001 is 1. So this is the 125 representation of octal from hexadecimal to octal. Like that you need to do the conversion if you come any kind of conversation from any kind of number system. Okay, so this is all about your conversation things. Okay, means how you will convert the number system from one form to another form. Now in the next you will see, in a number system only, binary arithmetic is there. Binary arithmetic means what? We have some arithmetic operation in a digital electronics. They will perform some arithmetic operation. Like if we talk about arithmetic, simple arithmetic, then we have what we will do generally in arithmetic. What we will do? We will do addition. Okay. Then we will do subtraction. We will do multiplication. And we will do division. Okay, this 4 thing basic we are doing in arithmetic. Okay, now here in digital we are dealing with 0 1 only. So we have 0 plus 0, then we have 0 plus 1, then we have 1 plus 0, and we have 1 plus 1. This 4 combination generally we have in a binary form. Okay, same in subtraction also, we have 0 minus 0, then we have 0 minus 1, 1 plus 1 minus 0, and 1 minus 1. This 4 combination. Same thing for multiplication also, 0 multiplication 0, 0 multiplication 1, 1 multiplication 0, then 1 multiplication 1. Okay, and division also, 0 division 0, 0 division 1, 1 division 0, and 1 division 1. So same like whatever we are doing general arithmetic, same thing we will do. 0 plus 0 is what? 0. 0 plus 1 is what? 1. 1 plus 0 is 1, and 1 plus 1. Here the thing is, only here 1 plus 1 is what? In a binary it is not 1 plus 1 is what? 2. 2 means what? 1 and 0. Okay. So 1 and 0 is there. It will come 1 and 0. 1 plus 1 is what? 1 and 0. So here we are writing as a sum as a 0, and we will write carry as a 1. This 1 is a carry. Okay, sum 1 plus 1 is 0, and 1 we have carry. Same for 0 minus 0 is 0, and 0 minus 1, like if we talk about 1 minus 0, so it will be 1, and 1 minus 1, 1 minus 1 is 0. Okay, for 0 minus 1. Generally, if we are doing subtraction, if anything like this is there, we will take one borrow. So we will take one borrow. One borrow means like here we will take one borrow. Here it is a binary representation, binary. So borrow is what? Borrow is 2. If you take borrow, that will consider as a 2. And 2 minus 1 is 1. And we have taken borrow, that will be considered as a 1. Okay. So always remember borrow we are taking as a 2, but we are not writing in a borrow is a 2 because it is a binary representation. This here we are taking borrow, so it will represent 1 like we have taken borrow as a 1. Here borrow we have 0, we didn't take borrow. Here also borrow is a 0. So here we are taking borrow, that's why it will be borrow we are considering 1. And for difference we are doing same process, whatever we are doing subtraction. So we have taken borrow, that will be your 2. So 2 minus 1 is your what? 1. Okay. So for this thing and this thing you need to remember this 2 point, and apart from that we have simple mathematics. So 0 multiplication 0, 0 1, 0 1 multiplication 0, 0 1 1 1. Simple thing. Then we have division also. So 0 division 0, it will be not defined as we have already studied in mathematics. So 0 division 1 is what? 0, and 1 division 0 is infinity, 1 division 1 is 1. So this is the simple arithmetic concept, like for arithmetic how we are doing this thing. Okay. Now we'll see some complement representation is there in a digital system. Like for complement representation, we have ones complement and twos complement. Okay, ones complement. Okay, if we talk about ones complement, suppose you have binary number 11001. Okay, we have binary number 11001 and we need to convert this thing in a ones complement. So for ones complement representation, simply we have to do complement. Like if you have 1, you need to write 0, 1, then 0. If 0 is there, you need to write 1. If 0 is there, you need to write 1. If 1 is there, you need to write 0. Okay, so this is the representation of ones complement. Okay, ones complement. Okay, now suppose if they will ask two's complement representation. Okay, two's complement representation of 11001. Okay, you have given this binary number. Now you have to represent as a two's complement. So for two's complement, what we will do? First we will convert this thing in a ones complement. So ones complement representation is what? 00110. This is the ones complement. Okay, ones complement. Now for two's complement, we need to add 1 here. In first we will do ones complement, and in a ones complement we will add 1 here. Okay. So 0 plus 1, 0 plus 1 is what? 0 plus 1 is 1, and here 1, 1, 0, 0. So this is what? This is two's complement representation of the binary number. Okay. So this is what? This is complement representation. Now if we talk about some other important code, is what? Like if you other important code, we have BCD. BCD means what? Binary coded decimal. Okay, binary coded decimal. Binary coded decimal, it will be represented by 4 bit. Okay, 4 bit representation. It is a 4 bit representation. In 4 bit we are generally represent the BCD. Okay, and this 4 bit is called as a 1 nibble. The 4 bit representation of a binary number is called 1 nibble. Suppose we have 0010. This is the 4 bit representation. So this is called, if like 4 bit representation is called 1 nibble in a binary system. Okay. or digital system. Okay, suppose suppose if we have 56 in a decimal number and we need to represent as a BCD. So BCD we have to represent by a 4 bit. So 4 bit representation of 6 and 4 bit representation of 5, as we have made table before from 0 to 50. Just from there you can write this one. 5, how we are representing? We are representing as a 0 1 0 1, and for 6 it will be 0 1 1 0. This is the BCD representation of decimal number. Okay, now the other code, if we see, another one is your access 3 code. Access 3 code we have. Okay, access 3 code. So access 3 code is what? Access 3 code we can obtain by adding 3 in a number. Okay, like you can write definition. We can obtain access 3 code by adding 3 in any decimal number. Okay, we can add 3 and we will get any decimal number. Suppose if you see the example, suppose we have 5 here. Okay, 5 given in a decimal. Now you need to convert this thing in an access 3 code. So 5 plus 3 you need to do. 5 plus 3 is what? 8, and you need to represent by a binary, that will be your 1 0 0. This is the binary representation of 8. So anything it will come means in a decimal form, you need to add 3, and after that you need to convert that thing in a binary form. Okay, now if we talk about another one, that is your fourth one, is your gray code conversation. Okay, gray code gray code conversation, what we will do? Gray code, they are generally used in digital signal to detect a error. If error is there in a signal, then we are using gray code. Okay, and okay, I will write, it will uh, it prevents error prevents errors in digital system. Okay, digital system. Okay, and it uses XOR gate. I will talk about gates and all later. Just remember this thing. It uses XOR gate. Now here we have conversation. First thing is how binary. If you have binary number, how you will convert binary to gray conversation. Okay. If any binary number is there, suppose you have 1101. This is the binary representation. Now you need to convert this thing in a gray code. Then how you are going to convert? So as I told, it uses XOR gate. So we have some rule for XOR that I will discuss later when we will discuss about gate and all. Just till means now you just understand this thing. If we will do XOR operation here with this digit, so if like if same thing is there in a, like same value is there, suppose you have 0 0, so in that case it will come 0, and if we have 1 1, means same thing is there, then it will come 0, and if we have different combination, like we have 0 and 1, then it will come 1. If 1 and 0 is there, then it will come 1. Means different is there, then it will come 1, and if same thing is there, and that case it will come 0. Okay, now we have binary 1101. Okay, now we need to convert this thing in a gray. So what we will do, this first part, first we will call it MSB, most significant bit, so that you need to write as it is, so it will be 1. Now you need to do this one and this one XOR operation. So 1 XOR 1, 1 XOR 1 is what? 0. Okay, so here it will come 0. Now from this 0 to this 0 you need to do XOR operation. So 0 XOR 0 is what? 0. Now this 0 to this one you need to do XOR operation. 0 XOR 1 is what? 0 XOR 1 is what? 1. So this will be your 1001, and this is what? This is your gray representation of this binary number. Okay, like this, same if they will ask from gray to binary. Okay, if they will ask same thing from gray to binary, if we have same number like if we have same number 1101, okay, if we have same number as a gray, now we need to convert this thing in a what? This is what? This is gray. Okay, this is gray. Now we need to convert this thing in a binary. So binary, you need to convert same thing. You need to first bit you need to write as it is 1. Then here you need to do XOR operation like this. Here you need to put XOR between these two. 1 XOR 1. 1 this one and this one. 1 XOR 1 is what? Sorry. We'll take this gray. Okay. Just a second. Okay, now we will take gray 1001 as we get this gray code here. Now we will check, we will convert this thing, and whether we are getting this number or not, we will see. So first bit you need to write as it is. Now we need to do XOR operation in between this. So 1 XOR 0, 1 XOR 0 is what? Is 1. Now from here to here, 0 XOR 0, 0 XOR 0 is what? 0. Now for this 0 XOR 1, 0 XOR 1 is what? 1. So this is what? Binary representation as we have discussed here. Same thing we have get here also. So this is the conversion from binary to gray and gray to binary conversion. Okay, some one more code is there, like 1 2, this will be your 3, and one more code is there, that is your ASCII code is there. Okay, ASCII code is what? American Standard Code Interchange Information Interchange. Okay, American Standard Code Information Interchange. Okay, this is the full form of this, and it will represented by 7 bit. Okay, it will represented by 7 bit, and it will represent from small a to capital A to Z, then small a to small z. Okay, for capital A to Z, we will represent from 65 to 90. Okay, A is a 65, Z is a 90, B is a 66, C is a 67. Like this, you need to go 90. Now, for small a, it will be 97, and for Z, it will be small z, it will come 1 2 2. Okay, so this is the range. Small a is 97, small b is 98, small c is 99. Like this, you need to go till 122. This is just for basic thing, like basic you need to know about this code conversation. Okay. Like sometimes they will ask general question, like they will ask what is the ASCII, what is the binary representation. If they will ask question, what is the binary representation of ASCII code A? Okay, what is the binary representation of ASCII code A? So binary representation, we need to find the binary representation of A. So A is what? A in ASCII code, A is what? A is our 65. Okay, now you need to 65 is what? In a decimal it will be 65. Now we know how to convert decimal to binary. You need to take this 65 and you need to do the division method, so you will get your binary number. If you convert this thing, just do this one, how much you are getting, just check. I think you will get 1 0 0 0 0 0 and 1. This is the representation in a binary form. Okay, nothing you need to do. A representation, we know A is 65 in a decimal form. Now we know also decimal to binary how we are converting. So take 65 and convert in a binary form. Suppose they will ask ASCII code of B, how you will convert this thing, means what is the binary representation of B. So B is what, 66 as a decimal. Now 66 you know how to convert in a binary. So like this you need to do. Okay, so that is about your number system and codes. Okay, now the next topic is what, next topic is our logic gate. Okay, next topic is our logic gate. So if we start means logic gate, if we talk about logic gate, so logic gate is what, logic gate is nothing but is a building block of a digital signal that perform basic logical function, operate on one or more binary input to produce a single binary output. Okay, it has some building blocks, means it has some design or something that will perform logical function and produce a single binary output. Okay, so if we talk about logic gates, if we talk about logic gates, then we have total 7 type of logic gate. Okay, first, that will be in a group, means first, like it will divided into 3 category. uh, First one is your basic gate, then we have universal gate. Okay, we have universal gate, then we have exclusive gate. Okay, now basic gate we have 3 types, that is your AND gate, OR gate and NOT gate. Okay, then if we talk about universal gate, universal we have NAND and NOR. Okay, now if we talk about exclusive gate we have XOR or XNOR. Okay, XOR we will write sometime like this also, and this will be like this also. This is the type of logic gates. Okay, total 7 type is there. This is 3, 2 and 2, total 7, but we have a group of basic gate. Universal gate we will be categorized in a group wise. So this is the group representation of a logic gate. Okay, now basic logic gate is what, our basic logic gate is, first we have AND gate. Okay, first one is what, first one is your AND gate. Okay, first one is your AND gate. If you see the symbol of AND gate symbol is like this. This is the AND gate symbol. Okay, we have two input A and B, and we have output, and that will be represented by A dot B. AND means dot. Okay, now this is what, this is symbol, and we have truth table for all the gates. So we have two inputs, that is A and B, and we have output, that is your y equal to A dot B. Okay, so it has two input, means we have 4 possibility, 0 0 0 1 1 0 and 1. So it is a multiplication. Dot means multiplication, so 0 dot 0 is 0, 0 1 is 0, 1 0 is 0, and 1 dot 1 is what, 1. So this is the truth table for AND gate. Okay, now another one is what, OR gate. Okay, so OR gate we have symbol like this. This is the OR gate. This is input A and B, and output will represent as A plus B. So A plus B, again, for if we see the truth table for this, A plus B. So 0 0 0 1 1 0 1 1. Okay, and this will be your, this is your 0, means 0 plus 0 is 0, 0 plus 1 is 1, and here 1 plus 0 is 1, and 1 1 is also 1. Okay, so this is the representation of this is the truth table of OR gate. Okay, now if we talk about our NOT gate, okay, the third one is what? NOT gate. So NOT gate representation means symbol is like this. Okay, in NOT gate we have only one input and one output. If we have A, then it will NOT gate means as it will called as an inverter also. Inverter also. So it will be invert the input. Invert the input means we have one input, so output will be complement. If we have 0, then it will become 1. Then if we have input as a 1, then output will come 0. So just it will invert the input. Okay, this is the basic gate. Now if we talk about universal gate, why universal gate? Because using this universal gate we can make any gate. Okay, any gate we can design using universal gate. Okay, our universal gate is what? First one is your NAND gate. Okay, if we talk about symbol will be your like this. AND gate is there. Okay, NAND means what? N plus N. N means not and not and. So one bubble will come here. So it will be A and B, and this is what? Y equal to A dot B. Okay, A dot B, it will be what? Not and. Not and means what? Complement. We need to put one complement. Now if we see truth table of this also, then we have two input and one output. So this will be your 0 0 0 1 1 0 1 1. Okay, and output will be A dot B complement. So it will be not and, so it is just opposite of and. If you see the truth table of and here, so it will be 1 only when both the input is high. Okay, so it is the opposite. We need to, for NAND gate we have to make opposite, means if it will be 1 1, both are 1, then it will become 0 and rest will be 1. It is the not and, means opposite of and. Okay, now second one is what? NOR gate. NOR gate, how we will represent NOR gate? It is also not or. Okay, we need to put one bubble here. So not or. A, B, Y equal to A plus B, and not means we need to put complement. Okay, one bar. So A, B, we have Y equal to A plus B bar. Now this one will be 0 0 0 1 1 0 and 1. Okay, now this is what? Opposite of all. Okay, or in all things, whenever any one is there, any high is there, then output will be high. So in OR gate it will become 0 0 and it will become 1. Okay, in NOR gate. Okay, it is opposite of OR, so it will be 1 and it will be 0 0. This is the truth table for NOR gate. Okay, now universal gate over. Now we have another one is what? Exclusive gate. Exclusive gate we have XOR. Okay, first one is what? First one is XOR gate. XOR gate, how we are representing XOR? We need to make OR gate first, and here we need to put one more thing, and this will be your representation of XOR gate, and Y equal to, we will represent like this. XOR is like this, and we can write A bar B plus A B bar. Okay, and if you see the truth table, it will be A B, Y equal to A XOR B. Okay, so we have seen before for gray conversation 1 0 and 1 1. So it will be what? Any one is there, means any input is high. Sorry, like if both are same, then output will be 0. Okay, if both input is same, then output will be 0. And if any odd number of high is there, then output will be 1. Like that we have XNOR. Okay, XNOR means what? Not XOR. Okay, not XOR. So here same thing, we need to put bubble for not A and B, and this we will represent as A dot P. Like this we are representing. Okay, it will be AB plus A bar B bar. Okay, now this will be your AB, Y equal to A XNOR B. So 0 0 0 1 1 0 1 1. So it is opposite of XOR. So truth table will be, if both are 1 means both are same, then output will be high, otherwise it will be low. So this is the simply your what? This is the simply your truth table. Okay. Okay, so this is the representation of all type of gates. Okay, and sometimes they will ask question from logic gate implementation. Okay, logic gate implementation, as I told you, we have two kind of universal gate, that is your NAND and NOR. Okay, NAND and NOR. We have two kind of gate, that is NAND and NOR. Using that we can make any kind of gate. Any kind of gate means we can make NOT gate, we can make AND gate, we can make OR gate, we can make XOR gate, we can make XNOR gate, we can make NAND gate, and we can make NOR gate. Okay, this all gate we can design using NAND or NOR. Generally in exam question will come using how many gates are required to implement NAND gate using NAND gate. How many gates are required to implement implement AND gate using NAND gate. Okay, like that question will come. How many gates are required to implement XOR gate using NOR gate? So for that I am giving you one table. Just remember this table. It will be helpful for lifetime. Means it will be, you will not forget this thing further. For NOT gate it will be always 1, it will be 1, then 2, then 3, then it will be 4, then it will be your 5, and NAND is there, so NAND we can't design using NAND, and it will be your 4. Okay, just remember this thing. Now what you need to do, this one you need to put here 1, and now you need to do cross. This 3 will be go here and 2 will be come here. Now again you need to make cross this one, this 5 will be come here, this 4 will be come here. Again same thing, you need to make cross here, this 4 will become here, and using NOR we means using NOR how we will design NOR. So not required this one. So this is the true not truth table, this is the table. Means question will come anything, you need to give answer using this table. Suppose any question will come, design NAND gate using design XNOR gate. If question will come, design XOR gate using NAND gate and tell how many NAND gate is required. To implement XNOR gate, how many NAND gate required? So total 5 gate required. How many XOR gate how many to implement XOR gate, how many NOR gate required? So 5 gate required. Okay, and if you want to see that diagram, so this is the diagram, universal logic gate using NAND gate. Okay, using NAND gate, like for AND gate, see AND gate only 2 gate is required. You can check here, using NAND gate how many AND gate required? So only 2 gate required. Okay, so here you can say OR gate 3 is required, 3 using 3 NAND gate we are implementing. So here you can check OR gate 3 is required. Okay, so this is the representation of NAND gate. Okay, you can make a note of this one also, and using NOR gate also, if you want to see using NOR gate also, it is there, and you can match with that table. Okay, so this is the representation of means what, implementation of gates using NAND and NOR. Okay, now technique. So logic simplification technique is what, it is the process to reducing the complexity of a Boolean expression or a logic circuit. Generally we have for design a logic circuit using logic gate and all. So our main aim to it will be reduce and will make with a less gate, number of less gate requirement is should be there. So for that we are using this logic simplification technique, and we have why it is required, because it will reduce the number of logic gates. Okay, first it will reduce the number of logic gates, it will minimize the hardware and it will improve the circuit speed and efficiency. Okay, that's why we are using logic simplification technique. And in this technique we have two kind of technique we are using generally. Simplification technique. Okay, if we talk about we have two kind of simplification technique. Okay, the first one is boolean algebra. Okay, and the next one is k-map. Okay, k-map, or you can say Carnot map. Okay, these two technique we are using to simplification for logic simplification. Okay, now if we will talk about our Boolean algebra. So in Boolean algebra is what? Boolean algebra simply it will deals with a binary variable and logic operation, and it will minimize or it will simplify the digital logic circuit. Okay. So for that we have some rule and regulation. We have some laws also for that Boolean algebra. So we will see one by one. First one is your basic laws. Okay, if we talk about basic law, that you need to means it will use everywhere while you are solving Boolean algebra. So basic laws is your a plus a, then a plus 0, a plus 1 and a plus a bar. Okay, so whenever you will get a plus a, this is the formula you can say. Okay, a plus a is what? A plus 0 is what? A plus 1 is 1 and a plus a bar is 1. Okay, similarly if you go for dot, a dot a dot a, then a dot 0, then a dot 1, then a dot a bar. Then for that a dot a is what? A dot 0 means 0, a dot 1 means a, and a dot a bar is 0. Okay, and whenever you will get double complement a double bar, that will be equal to a. Okay, this is the basic, law. Okay, now if you go for more laws, we have total 5 or 6 laws in this Boolean algebra. Okay, so now the second one is your commutative law. Commutative law. Okay, in this if you will get a plus b, then you can write this like a b plus a. Okay, if you get a dot b, then you can consider as a b dot a. This is what commutative law. Okay, now the third one is your associative law. associative associative law. Okay, in associative law, if a plus b plus c is there, you can write a plus b and plus c. Okay, similarly a dot b dot c is there, you can write a dot b dot c. This is what associative law. Then we have distributive law. Okay, distributive law. In distributive law, if you have a dot b plus c, then you can write this one ab plus ac. Okay, this is what distributive law. Then we have absorption law. So in this, a plus ab is equal to a, and a plus b is equal to a. Okay, this is the law. This means you can consider as a formula also, and this is simple law, just you need to remember. And the main law is what? De Morgan law. De Morgan's law. Okay, De Morgan's law. In De Morgan's law, if we have a dot b and bar, then we can write this one a bar plus b bar. Okay, and if you have a plus b bar, then you can write this one a bar dot b bar. This is what? This is De Morgan's theorem or De Morgan's law. Just remember this all point for solving questions, means for Boolean algebra reduction. Okay, suppose if you have f equal to ab plus a bar b. Okay, if you have given this one and you need to reduce this one using Boolean algebra method. So what you will do here, you can see here you have b as a common. You can take b as a common, and this one a plus a bar. Okay, and just now we have seen that basic law, a plus a bar is what? 1. So it will be what? B dot 1, and that is equal to b. So your answer will be what? B. Okay, now suppose if we go for a large one, suppose f equal to a b bar and plus a bar plus b bar plus c dot c bar. Okay, and we'll make full bar. Okay, this is the question. We need to reduce this one. Now you can write a b bar like this. Then here you can write a bar plus b bar and plus c dot c bar, c dot c bar. So we have seen a dot a bar in the basic law. A dot a bar is what? A dot a bar is 0. So similarly, c dot c bar is nothing but 0. Okay, so it will become 0. Okay, now you have like this a bar plus b bar ka whole bar. Now we can use our De Morgan's theorem here. So if you have a plus b bar in De Morgan's law, using De Morgan's law, we can write a dot, means a bar dot b bar, like that we can write. So here also you have a bar, I mean full bar is there, we can remove that full bar. So we can write a, already bar is there, so one more bar will come and this will be dot. So like this it will come. Now you can write a bar plus a double bar is what? A, and b double bar is b. Okay, so here you can take common as a and b bar plus b. So now b bar plus b is what? B bar plus b is nothing but 1. So it will be a dot 1 and a dot 1 is a. So your answer will be a. Like this, if you will get like this what? Boolean algebra, then you need to solve like that. Okay, so this is the Boolean algebra technique. Now we have Carnot map, that is K map, another simplification technique. So this is what? This is nothing but this is your graphical representation of a Boolean expression of 2, 3 and 4 variable. Okay, this is the graphical method. Here we will make a graph, and using that graph we are reducing the number of logic gate. Okay, so it will be applicable for 2, 3, 4 and means till 6 variable, but we require 2, 3 and 4 till 4 only. Basically they will ask in a exam. So first we will see for 2 variable. Okay, so for 2 variable, how you will design f a b. Two variable means AB only. So for that, if 2 is there, then 4 column required. Okay, so here it will be, you can write this one A and this one B, and this is what, this is your 0 and this is 1, this is 0 and 1. So this one is your B bar and this one is your B, this one is your A bar and this one is your A, and this box number is, this one is 0, this one is 1, this one is 2 and this one is 3. Okay, this is two variable representation of a CAM app. Now for three variable, okay, three variable, that means what, f is A, B and C, that is your three variable. Three variable means 8 box you need to make. So like this you can design your box. Okay, and this one is your 1, 2, 3. So here you will get 8 box. And here you can write this one is A and this one your B and C. So this is two variable this side. So you need to write here 0, 0, 0, 1, then 1, 1 and 1, 0. And here this side, this is one variable. So it will be 0 and 1. Now, how you will make box representation? So here first this 0, 0 means what? This is B bar, C bar, this is B bar C, this is B C, this is B and C bar, this is A bar and this is A. Now here this one is 0, this is 1, this is 2, 3, 4, 5, 6 and 7. So like this for 3 variable. Now for 4 variable we'll see. For 4 variable, it will become like this. 4 variable means what? 4 variable means F, A, B, C and D. That is your 4 variable. 2 to the power 4 is 16. So 16 box we need to make. So 1, 2, 3 like this. 1, 2 and 3. Okay, now this will be your AB and this will be your CD. Okay, C and D. Okay, CD. Now this one is your two variable means 0, 0, 0, 1, 1, 1 and 1, 0. This side also two variable, so 0, 0, 0, 1, 1, 1 and 1, 0. Okay, 0, 0 means C bar and D bar. Okay, 0 means bar. Then this is C bar, this is D, C and D, C, D bar. Okay, now this is your A bar, B bar, A bar B, A and B, A, B bar. Okay, now for numbering, this is your 0, 1, 2, 3, 4, 5, this is your 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. So like this numbering will be there for 4 variable. Okay. So now before solving this K map, you should know about conical form. Conical form is nothing but it is the standard form. Okay, conical form or standard form both are same. We have two type of conical form or standard form. Okay, first one is your SOP and POS. SOP means what? Sum of product. Okay, and POS means what? Product of sum. All right. Now SOP, sum of product. If you see the sum of product, how we are writing? F A B C. For three variable, it will be A bar B bar C plus A B bar C plus A B C. For example, this is the example of SOP, sum of product. Here all sum is there, so sum of product. This is the product. So sum of product. Now you can represent this thing using number also. Bar means 0, bar means 0, this is 1, and plus this is 1, this is 0, 1, plus 1, 1, 1. So 0, 0, 1 is what? 0, 0, 1 is your 1, and plus this is 5, and plus this is your 8, sorry, 7. Okay, this is your 7. Okay, so you can write this one f a b c f a b c is equal to summation of m 1 5 7. Okay, this is m is what? M we called mean term. Okay, so sometime you will get question in a number form, or direct you will get in a expression form. Okay, so like that you need to represent in both way. Now, if you see POS, POS means what? Product of sum. So, product of sum is for three variable A, B, C. Okay, for A, B, C, we will take one example again. So, you can write A plus B plus C, A bar plus B plus C, and A bar plus B bar plus C. So this is what here product is there and sum is there. So product of sum. Now here different means POS. If you get POS product of sum, in this product of sum you need to make opposite means if A is there, no bar is there, then here bar means 1. Okay, in POS bar means 1, and without bar means 0. So this is 0 plus 0 plus 0. Okay, and this is 1 plus 0 plus 0, and this is 1 plus 1 plus 0. All right, now this is what you can means this one is 0, and this is what? This is 1, and this is 6. Sorry, this is 4 and 6. So f a b c is equal to summation of 5 0 4 and c. This is called max term. Max term. Okay, so like this in QS we are representing our number and expression. Okay, just remember all these things. All right, now if you solve one question, we'll take one example. Question will take from SOP, sum of product for three variable. Suppose in a question it is given f a b c is equal to ab plus a b c and plus a bar bc plus a bar b c bar. Okay, suppose we have given this question, we need to solve this one. We need to make it SOP, and after that K map, using K map we have to reduce this one. So AB here SOP means, sorry, conical form or standard form means what? In a expression, first you need to check before solving a K-map question. In a expression, you need to check all are. Suppose you have three variable, so all terms should be in a three position. Here it is like AB is there, means two position is there. ABC is three position. Here also three position. Here also three position. So this AB we need to make as a three position. How we will make three bit? So A B, here C is missing, so we can write C plus C bar. Okay, because C plus C bar is what? 1. Okay, C plus C bar is 1, so we can assume here 1 is there, so 1 is 1 equal to what? C plus C bar. Now ABC plus A bar BC plus A bar BC bar. Now we can write this one A BC plus A BC bar plus A BC plus A bar BC plus A bar BC. Now you can check this one. Here if you get common like this thing and this thing is common, so make it 1 A B C plus A B C bar plus A bar B C plus A bar B C bar. Now no common term is there. So now you can see all are in a 3 form. Okay. Now you need to make a number. So it will be what? 1 1 1 plus 1 1 0 plus 0 1 1 plus 0 1 0. Okay. Now you can write F A B C, that is summation of mean term. Okay, in SOP it will be mean term, and POS it will be max term. So 111 is what? 7. This is 6. This is your 3. Sorry, this is your 2, and this is your 010. 010 is 2, and this is 3. 011 is 3, this is 2. Okay, just check that table I explained before. So 7 6 3 and 2, this is what? Representation of SOP in a number. Now you need to solve this one using K-map. We need to reduce this expression. So this is 3 variable. 3 variable means we need to make one K-map like this. For 3 variable we are designing 8 box. Okay, so here 8 box will be there, and this is A, and this is B, and this is C. Okay, 0 0 0 1 1 1 1 0. This is 0 and 1. Now this is 0, this is 1 2 and 3 4 5 6 7. Now whatever term is there you need to make as a 1. 7, so in 7 this is 1. 6, here you need to put 1. 3, here you need to put 1, and 2, here you need to put 1. Now for K map you need to, in the K map you need to make either pair, either quad, or either octal. First priority is octal, after that quad, after that pair. Okay, so here octal is not there, so we can make a quad here. So here we can make one quad, and now we need to write a equation. So this is A bar, and this is A. This is B bar, C bar, B bar, C, B C, B C bar. Okay. Now here you need to find the common term. If you go this side, vertical side, so A bar and A both are different, so no need to write that one. And now from these two boxes, from these two we need to take a common term, like here BC and BC bar is there, so here common is what? B. So here F equal to what? B is your answer. Like this you need to solve K map. Okay, now if we take question for POS, product of sum, so F, here we will consider 4 term. Okay, 4 variable A B C D, will solve 4 variable. Okay, so suppose you have A B C D, then A B C bar D, or you have A bar plus B plus C plus D, and A bar plus B C bar plus D. Okay, this is what? This is the question. We need to solve this one. So in POS, I told you this is already in a 4 form. All are in a 4 bits. So no need to make it is 4. Okay, all are in a standard form. Now I told you in POS, if it is a product of sum, then bar means 1. Okay, and without bar means 0. So 0 plus 0 plus 0. Okay, and here this is 0 plus 0 plus 1 plus 0. Here 1 plus 0 plus 0 plus 0, and here 1 plus 0 plus 1 plus 0. 1 plus 0. Okay, now you need to write F A B C D summation of max term. Okay, summation of, in product POS we will write max term. So 0 0 0 is what? It is 0. This one is 2. This one is 8 and this one is 10. Okay, this is the representation in a number form. Now we need to make a K-map table. 4 variable means we need to make a 16 box. Okay, so we'll make 16 boxes like this. Okay, so this one, and this one. Okay, now this is what AB and this is what CD. Okay, so 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. This is 0 1 2 3 4 5 6 7 8 9 10 11 and 12 13 14 15. Okay, now here we need to put 0. Okay, as in SOP we are putting 1, here you need to put 0. For 0, so 0 2 0 8 0, now 10 0. So these 4 boxes we can make a quad. Like this we need to make a quad. Okay, here we can make a quad. Okay, now this is what C, sorry, this is plus, this is plus, this is plus, and this is plus, means C plus D. Okay, 0 means no bar. C plus D bar, then C bar plus D bar, and this is your C bar plus D. Okay, here A plus B, here A plus B bar, and here A bar plus B bar, and here A bar plus B. Okay, now we have we made a quad, so you need to find a common term. So first we'll check in this two what is the common. So here you have common term B. B is a common, so this side you need to write B, and plus this side we'll check these two. Here what is the common? So in this D is a common. Okay, so you need to write D. So this is the answer for this K-map. Okay, don't be confused in this what bar and all. In in SOP you need to put 1, and POS you need to put 0. Okay, in SOP bar means 0, and in POS bar means 1. Okay, that thing you need to remember only. And here in SOP you need to go for dot, and in POS you need to go for plus. Okay, this is the K-map, means simplification technique. Here simplification technique will complete it. Now our another topic is what? Logic circuit. Okay, logic circuit are the fundamental building block of digital electronics. They are used to perform logical operation on a binary input to produce binary output. Okay, so logic means it has some design and some block which are used for a particular function of a for a logic operation. Okay, so generally our logic circuit is divided into two types, that is our combinational circuit and sequential circuit. Okay, two type we have different kind of circuit, and we have categorized into in a two way: logic combinational logic circuit and sequential logic circuit. Okay, if we see the difference between this combinational and sequential, so combinational circuit is what? Combinational circuit is what? Which output is depend only on the present input. Only it will output will depend on only present input. And for sequential circuit, output depends on present input and as well as past output also. Okay, this is the main difference between combinational circuit and sequential circuit. And in a combinational circuit there is no need of memory element, but sequential circuit has a memory element. Here also in combinational no feedback required from output to input, but in sequential circuit it has feedback from output to input. And it combinational circuit, it does not depend upon any clock signal. but here it required clock signal in sequential circuit. Some example, if you see example for combinational, we have adder, subtractor, multiplexer, encoder, decoder, and comparator. Okay, comparator. So these are called combinational circuit. Sequential circuit, we have latches, flip-flop, counter, shift register. They are sequential circuit. Okay, so we'll discuss all one by one. First, we will start with combinational logic circuit. Logic circuit, we have adder circuit. Okay, adder generally we have two type. Okay, adder we have two type. First one is your half adder circuit. Then we have full adder circuit. Okay, half adder and full adder. If we talk about half adder, half adder means what? Addition. So half adder, it will add 2 bit. Okay, it will add 2 bits. Half adder is used to add 2 bit, and it has 2 input and 2 output. If you see the block diagram, it has AB as the input and it has 2 output, that is, one is sum and one is carry. Okay, so this is what half adder. Okay, if you see the circuit diagram for half adder, circuit diagram will be like this. This is XOR gate. Okay, this is your input A and B. Then we here that it will calculate sum, and here one AND gate required for carry. Okay, same, this A will be go this side and this B will be go this side. This is what? Carry. So sum will be, you can calculate this sum. This is XOR, you know XOR operation. So sum is A XOR B, and carry is what? A and B. Okay, now if you see truth table for this also, so your truth table will be like this: A, B as the input and sum, carry as a output. Okay, this is your input side and this is your output side. Okay, now 0 0 0 1 1 0 and 1 1, this is the condition. So we know addition, we have seen before addition, how addition will happen. So 0 plus 0 is what? 0 and carry 0. 0 plus 1 is what? 1 and carry 0. 1 plus 0 is what? 1 and carry 0. 1 plus 1 is what? 0 and carry 1, as we have discussed when we have discussed about arithmetic operation before starting of the class. Okay, so same thing I applied here. Okay, so the equation will be like this: for sum, A XOR B, and for carry you need to write A dot B. This is the expression. Okay, now if we talk about our second one, that is your full adder circuit. Okay, full adder circuit. In half adder we are adding only 2 bit, but in a full adder it adds 3 bits. Okay, it's add 3 bits. Okay, so it has 3 input. This is full adder and it has 3 input. Okay, A, B, and another one is C in, that we call carry in, and output will be 2 only, that is your sum and carry. Okay, this is your output. Now if you see the block diagram here also, you have to design like this. This is your XOR gate. Okay, then this one is your input A and this one is your input B. Okay, here you need to make one more XOR gate because it has 3 input. Okay, one XOR, this C in will go here. Okay, this is what? C in. And now for carry you need to make one AND gate like this here. Okay, it will be connected with this one, and this will be connected here. Okay, this is AND gate and one more AND gate required. Okay, and it will be connected with this A and B. This is your A and this one is your B. Okay, this one, and one OR gate required. To combine this, one OR gate required. Okay, this is what carry out, and this is what, this is sum. Now if you design your truth table, so it will be A, B and C in, okay, and output side will be one is sum and one is carry. Okay, now this is what, this is your input side and this is your output side. Okay, like this you need to write. So 3 bit is there, so it will be 0 0 0 0 0 1 0 1 0 and 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. Okay, I told you how to write table. So 0 plus 0 plus 0, 0 plus 0 plus 0 0, then 0 plus 0 0 and carry is 0. 0 plus 0 0, then 0 plus 1 is 1 and carry 0. 0 plus 1 is 1, 1 plus 0 is 1 and carry 0. 0 plus 1 is 0 and 1 plus 1 is what? 0 and we have carry 1. Same thing. 1 plus 0 0, 0 plus, sorry, 1 plus 0 1 and 1 plus 0 is what? 1 and carry 0. 1 plus 0 is 0, 1 plus 0 is 1 and 1 plus 1 is what? 0 and carry 1. 1 plus 1 is 10, that is 0, means 10. 10 plus 0 is what? 0 and 1 carry. Okay, then 1 plus 1 is 10, 10 plus 1 is 11, so 1 and 1 carry. So this is the truth table. Okay, now if you see the equation, so for sum it will be, you can see here, sum you will get this, like if you write a expression according to this table, then it will come A XOR B XOR C in. Okay, and for carry, if you see the truth table for carry, it will come AB plus BC in and plus AC in. Okay, this is the equation for a full adder. Okay, now we have subtractor also. Okay, we have subtractor circuit also. So in subtractor circuit, subtractor, addition is what? Addition for add the bit and subtraction for subtract the bit. So here also we have two type of subtractor. First one is half subtractor. Okay, half subtractor. Half subtractor, what it will do? It will perform subtraction of two single bit. Okay, it will perform subtraction of two single bit. Okay, two single bit, it will perform subtraction for the two single bit. If you check here, it has also half subtractor, it has also two input, that is your A and B, and subtraction means we will get difference, and one it will come borrow. Okay, borrow, that we have discussed before also. So if you see the circuit diagram, here also it required XOR gate. Okay, here also it required XOR gate for difference. This is your A, this is your B, and here we need one AND gate, same as a adder, but for AND gate here we required one more NOT gate. Okay, like this diagram will be there for half subtractor. This is what? Borrow out. Now you can check your truth table also. A, B and output is your difference and borrow out. Okay, so here this will be input side and this will be your output side. Okay, 0 0 0 1 1 0 and 1 1. So now we have to do subtraction. So 0 minus 0 is what? 0, borrow 0. 0 minus 1 is what? 0 minus 1. So we need to take 1, borrow, and 2 minus 1 is what? 1, as I discussed before, subtraction wala. Then 1 minus 0 is 1, borrow 0. 1 minus 1 is 0, borrow 0. This is simple truth table. Okay, now for D is D, you can see this is what? XOR table. So A XOR B. And for B node, that is borrow node, output is 1 here only when A bar and B is there. Means A bar B. Expression will be like this. This is what? Half subtractor. Okay. Now, if we see another one, that is your full subtractor. Okay. Now, full subtractor. Full subtractor, what it will do? It will do 2 bit also and one input here. It will subtract. Okay. It will subtract 2 bits with borrow in borrow in input. Okay, you can write like this. It will subtract 2 bit with borrow in input, means it has 3 input. Okay, it has 3 input. This is what? Full subtractor. We have 3 input, A, B and borrow in. Okay, and output we have 2, that is your D, means difference, and borrow out. Now we will design the circuit diagram. So here same is a full ladder. We required 2 XOR here also. Okay. So here 2 XOR we required like this. Okay, 2 XOR, and apart from that, same as this is what? This is your borrow in. This is A, this is B, and this is borrow in. Okay, and same like our full ladder, we need to make here AND gate also. AND gate, this is also AND gate, and it will be connected with OR gate. Okay, sorry, this is not, this is OR gate. Okay, OR gate, this bubble will be not there. OR gate. Okay, so OR gate, and it will connect like this will come here, and here we need to put one NOT gate, like subtractor we have done. Okay, and this will be this will, sorry, this will connect here. Okay, and now one we need to require this one wala, it will come like this, and here we need to put NOT gate and like this, and then one B it will come in this input. This is the circuit diagram of full subtractor. This is difference, and this is what? Borrow out. Okay, now we'll see the truth table. So A, B and B in is a input, and we have output D, that is difference, and one more thing, that is borrow out. Okay, so 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. Okay, this is the number. So now we will do subtraction. 0 minus 0, 0 0 minus 0 minus 0 0, then 0 minus 0 is 0 and borrow 0. 0 minus 0 0, and 0 minus 1 is what? We need to take one borrow. So 2 minus 1 is 1. 0 minus 1, we need to take one borrow. So 2 minus 1 is 1, and 1 minus 0 is 1. Okay, 0 minus 1, we need to take one borrow, and 2 minus 1 is 1, and 1 minus 1 is 0. Okay, now 1 minus 0 is 0, 0 minus 0, sorry, 1 minus 0 is 1, and 1 minus 0 is 1, and borrow 0. 1 minus 0 is 1. Okay, 1 minus 0 is 1, and 1 minus 1 is 0, and borrow 0. Now 1 minus 1 is 0, 0 minus 0 is 0, borrow 0. 1 minus 1 is 0, and 0 minus 1, we need to take one borrow, and it will come 1. Okay, 2 minus 1 is 1. Now this is the truth table for full subtractor. Now for expression, if you go for expression, then difference will be same, A XOR B XOR B in. Okay, and for borrow out, borrow will be A bar B. Okay, this one only, A bar B plus A bar B in, and plus B dot B. Just remember this expression, they will ask sometime direct expression of this. Okay, now you need to remember just 2 points, like using two half adder. Using two half adder, we can design full adder. Okay, full adder. All right, and using two half subtractor, we can design full subtractor. Okay, all right. Just remember this 2 points. Now coming to next topic, next point, that is your multiplexer. Okay, it is also combinational circuit. So multiplexer means what? It has many input and one output. Sometimes it is called as a mux also. Okay, so it has many inputs and single output. Okay, and it uses select line. It uses select line to appear to forward, you can say, to forward inputs to the output. Okay, so this is the definition for multiplication. If you see the block diagram, its block diagram will be like this. Suppose we have 4 into 1 mux. Okay, 4 into 1 mux. Whenever mux will be there, they will represent like this. 4 means many input. 4 is there. So you need to make 4 line as an input. This is the input. And 1 means one single output. 4 into 1. Like that they will ask 8 into 1, 64 into 1. Like that multiplexer will be there. So here it will be I0 input, I1, I2 and I3 as an input. Now I told here they will use select line. So select line will depend upon the input. Input you have 4 means it will be 2 to the power 2. So this 2. Okay, this 2 you need to make here select line. So this is your select line, and select line will be your, this is S0 and S1. This is 2 select line because input we have 4, so it will be 2 to the power 2. So this we required this power. So this one is S0 and S1. This is called select line, and this we have output. Okay, now if we design our truth table, then truth table will be like this: 0 0 0 1 1 0 1 1. Okay, now I told you in definition it uses select line to forward input to the output. So whenever select line will be 0 0, whenever a select line will be 0 0, then it will forward I0 in the output. Okay, and when it is 0 1, then it will forward I1. When it is 1 0, then it will forward I2, and when it is 1 1, then it will forward I3. Okay, now you can design Boolean expression also using this truth table. Boolean expression. So Boolean expression will be y equal to s1 bar, y equal to s1 bar, s0 bar with I0. Okay, then plus from this side. This is what? S1 bar and S0 with I1. Okay, now this one is what? S1 and S0 bar with I2. Okay, now come this one. This one is what? S1 and S0 and I3. This is the expression for 4:1 multiplexer Boolean expression. Okay. Now, sometime they will ask question like this in this multiplexer. Generally, they will ask this question. This is very important question in most of the exam. They will ask like how many 2 into 1 mux is required to design 32 into 1 mux. Like that question they will ask. How many 2:1 mux required to design 32 into 1 mux? How many 4:1 mux required to design 64 into 1 mux? how many m into 1 marks is required to design m into 1 marks, like that they will ask question. So anything they will ask, you need to do one thing that I will tell you how to solve that one. You just check what you need to design. You need to design 32 into 1 and using 2 marks, means 2 marks. How many 2 marks, 2 into 1 marks is required. All right. So 32 you need to take here, 32, and this 2 you need to take here. 32 divided by 2 is equal to what? Is 16. Okay. Now you need to take this 16. So 16 divided by 2 is what? Is 8. Now you need to take this 8. 8 divided by 2 is what? 4. And this 4 you need to take here. 4 divided by 2 is what? 2. And again this 2 you need to take here. 2 divided by 2 is equal to 1. Okay, so you need to divide with 2 till it will become 1, or till after that it will not divide. From that much you need to do division. Anything is there, suppose here 64 is there, here 4 is there, then 64 by 4, like that you need to start. So in the first stage you need to design, you required 16 2 is to 1 marks. Okay, and now the second stage you need 8 into 1 marks, 8 2 into 1 marks required. Now in the third stage you required 4 2 is to 1 marks. Okay, now in the fourth stage you required 2 2 into marks, 2 into 1 marks, and in the last stage you require 1 marks. Okay, now you need to just add all this, you will get 31. Okay, so total 31, 2 is to 1 multiplexer required to design 32 into 1. Okay, this is the answer for this. Whatever question you will get, suppose 4 into 1, you need to design like 256 into 1 marks you required. Then you start with 256 divided by 4, and like this you do, and last you add all these things, you will get the answer. Okay, and one more trick is there here for 2 is to 1 marks only. Okay, for 2 is to 1 marks only, if they will ask any question using 2 is to 1 marks, you need to design any kind of multiplexer. You just need to do, if they have asked 32, so you just need to do 32 minus 1 is 31 is your answer. Suppose they will ask how many multiplexer required using, how many 2 is to 1 multiplexer required to design 64 into 1 marks, then 64 minus 1 is 63 your answer. Only for 2 is to 1 marks it will applicable. Apart from that you need to follow this method. Okay, now we'll talk about demultiplexer. Okay, one more thing about multiplexer. Okay, all thing over. Now demultiplexer. Demultiplexer, multiplexer is what? Here you can see it. What it have? It has many input. Okay, it has many input. It has many input means it has many input, and after that it is getting one single output. So we can say this is also used as a, or this is also called as a parallel to serial converter. Okay, just remember this point. Now the demultiplexer, in demultiplexer it has single input, it has single input and many outputs. Okay, and here also it uses select line, it uses select line to appear inputs in the output. Okay, it uses select line to appear input in the output. Now suppose same thing we will design 1 is to 4 marks opposite. Okay, so 1 is to 4 d marks. Okay, d marks, it is also called as a d marks. Okay, so 1, here 1 input, because 1 into 4 is there, so 1 input, and for this side means 4 output we required here, 4 output. So this is your I0 and this is your y0, y1, y2 and y3. As I told, it uses select line, so we required here 2 select line because it is 4. So 4 means 2 to the power 2 is equal to 4. So this is 2. So this one is your S1 and S0. Okay. Now if you see the truth table, for truth table, this is your S1 and S0. And output here we have 4 output we have. Okay. Here we have 4 output. That is your Y0, Y1, Y2 and Y3. Now, when it will be 0, 0, 0, 1, 1, 0 and 1, 1. This is the condition. So, when it will be 0, 0, then I will appear here. Okay. This I will appear here and rest will be 0, 0. When it will be 0, 1, then it will appear here and rest will be 0. When it will be 1, 0, then it will appear here and rest will be 0. When 1 1, then it will be 0 0 0 and it will appear in Y3. Y3 will appear in the input will appear in the Y3. Okay, so this is the truth table, and now you need to make expression, Boolean expression. So for Y0, Y0 is what? When it will be Y0, when this one will be S1 is bar, S0 is bar. So that time this I is appearing. Now for Y1, when S1 is bar and S0, then I is appearing. Then for Y2, this will be your S1 and S0 bar, then I is appearing. Now for Y3, it will be S1 and S0 and I is appearing. So this is the output expression. Okay. And same thing here also you can make a notes like as I told, multiplexer is used as a parallel to serial converter. Here you can demultiplexer is used as a serial to parallel conversion or converter. Okay, just remember this points. Okay, so this is about your demultiplexer. Now we have another combinational circuit that we call encoder circuit. Okay, so encoder is what? Encoder is encoder is you can consider as a multiplexer only, but the difference it has it has maximum of 2 to the power n input. Okay, 2 to the power n input line and n output line. Okay, it has 2 to the power n input line and n output line. Okay, so it has, as I told you, suppose we will design 4 into 2, 4 into 2 encoder. So 4 into 2 encoder, 4 into 2 encoder, like n here 2 into n, like this we need to write for encoder. Okay, so n here, n is what? N is 2. So n is 2, so this 2 to the power n is what? 4. So here we required 4 line and here we required 2 line. Okay, so this is what? This is your I0, this is your I1, this is your I2 and this is your I3 and this is your Y0 and this is your Y1. Now if you see the truth table, so input side it will be I0, I1, I2 and I3, and output side it will be Y0 and Y1. Okay, now this is 0 0 0 1 1 0 and 1 1. Okay, now it will encode only one at a time. Suppose like when I0 is here, means when 0 0 is there, means encoder, in encoder only one bit high at a time. Just remember, only one bit at high at a time. In an input, one bit only it will get high. Suppose I0 is there, so it will get high. Okay, it will get high and rest will be go 0 at the time of 0 0. Now here it will be 0 and this will be high. Okay, here it will be 0 and this will be high, and here it will be 0 and this will be high. This is the truth table for encoder, 4 into 2 encoder. If you see the expression, so for Y0 you need to write for Y0. So for Y0 it is going to high y0 is high when it will be here it will be 1 and here it will be 1. So when y0 is getting 1 when I2 is high and I3 is high. So you need to write I2 plus I3. This is the expression for y0. Now for y1 you need to write a expression. So y1 is getting high here and here. So y1 is high when I1 is there and this one I3. So I3. This is the expression for y0 and y1. Suppose they will ask question to design this one. So this is OR operation. You need to make OR here. Okay, and one more OR is required. You need to make OR here. This is what? This is sorry, not like that. We have two output, right? So we need to design two output. We need to design here. This is OR gate. This is one more OR gate. Okay. So here we have common input, that is your I3. Okay. And we have I2 and we have I1. This is your I2 and this is your I1. This is your Y0. This is your Y1. So here you can get I2 plus I3 and here you will get I3 plus I1. This is the expression, means this is the logic diagram. So using this expression you can design your diagram. Same we have discussed here also. You can design here using AND gate, and here also in multiplexer we can design with AND gate. Okay, because it is dot operation. Dot operation means AND gate and plus means OR operation. Okay. So this is what? This is encoder. Now decoder circuit. Decoder circuit means what? It has an input. It has an input line and 2 to the power n output line. Okay, decoder. It has an input line and 2 to the power n output line. Suppose we'll talk about 2 to the power 4 or n into 2 to the power n decoder. So 2n into 2 to the power n decoder means what? It has 2 input and 4 output. Okay, so input will be your I0, I1, and this one will be your Y0, Y1, Y2, and Y3. So this is your 2 into 4. Okay, now if you see the truth table will be I0, I1, and output will be Y0, Y1, Y2, Y3. Okay, and this will be your this is your input side. So this is 0 0 0 1 1 0 1 1, and same here output will appear one at a time. So when it is 0 0, then it will high 1 will be appear in y0, rest will be 0. Here it will be 1, rest will be 0. Here it will be 1 and rest will be 0, and this is your 0 0 0 and this is your 1. Okay, only one bit at a time. Now if you see the logic diagram, so for y0 is what? Y0 is getting high here when the condition is this one, means I0 bar and I1 bar. That time it is getting 0. And y1 is this side. Y1 when it is getting high when I0 bar is there and I1 is there. Same like y2 is what? Y2 is here. This is I0 and this one is I1 bar. Same for y3. Y3 is what? It is your I0 and this one is your I1. So this is the logic expression for decoder circuit. Okay. Now about comparator. Comparator is what? It compare two bits and produce the output. It compare two bits and produce output, single output. Okay, it will compare two bits. So if you see the diagram, your diagram will be like this here. This is your A and B. Two input is there, A, B, and it has three output. Okay, it has three output. First one is your A greater than B, A equal to B, and A less than B. Okay, so here if you see truth table, input we have two A, B, and output we have A greater than B, A equal to B, and A less than B. Okay, so just we need to do the simple logic 0 0 0 1 1 0 and 1 1. Now when it will be 1, when it is 0 0, 0 0 means what? This condition will 0, and 0 0 means both are equal, so this is high and this is also 0. 0 1, A is less than 1, A is less than 1 means this one will be high, this is 0, this is 0. Now here you can say A is greater than 1, so A is 1 and B is 0, so A is greater than 1, A is greater than B, so this is high and rest are 0. Now again here 1 1 1 1 means both are equal, so it is equal, and this side 0 0. Okay, now you can design your logic expression. After logic expression you can design logic diagram. Okay, so just you need to know about logic expression. So for A greater than B, for A greater than B, this is high. When A and B bar is there, that time it is getting high. Now for A equal to B, for A equal to B, two condition is there, this one and this one, means when A bar B bar is there and when A and B is there. This is the expression, we know this is the expression of XNOR. And for A is less than B, A is less than B is what? A is less than B is here. So when it will be A bar and B is there, then it is what? It is going to be less than B expression. So this is what this is about comparator. Okay, so this is all about your combinational circuit. I explained everything about combinational. Okay, is your sequential logic circuit. So as we have discussed about combinational, as we have discussed about combinational circuit, so in the combinational circuit its output depend on only the present input. Okay, but in the sequential circuit output will depend upon in present input as well as the past input. Okay, and in the combinational circuit there is no memory and no feedback. Okay, but in a sequential circuit if we add these two things in a combinational circuit, memory and feedback circuit in a combinational circuit, then it will become sequential circuit. Okay, sequential circuit. All right, so basically we have two types of sequential circuit. Okay, basically we have two type of sequential circuit. First one is your asynchronous sequential circuit, and the another is your synchronous sequential uh, sequential circuit. Okay, asynchronous sequential circuit is what? It not it not uses clock clock signal. Okay, it not uses clock signal like latches. Okay, then sequential means it uses clock signal. Okay, it uses clock signal. Okay, its example is what? Its example is flip flop. Okay, flip flop. So this is the two type of sequential circuit. We will discuss about asynchronous and synchronous circuit also. So our first we will start with asynchronous, that is latches. Latches is what? Latches is a basic memory element. Okay, it is a basic memory element that can store 1 bit of data or information. Okay, Latches is a basic memory element that can store 1 bit of data or latches. Okay, it uses label trigger. Okay, it uses label trigger. It uses label trigger. Okay, and we have some type of latches also. Type of latches. If we see the type of latches, we have SR latch. Okay, we have SR latch. We have JK latch. We have D latch, and we have T latch. Okay, T latch. Okay, this is what set reset. This some scientist name is there, and this is what delay, or you can say data or delay latch, and this is what toggle. This is toggle latch. Okay. Now latches can design using NAND gate and NOR gate also. Okay, it can design with NAND gate and NOR gate. Okay, it can design with NAND gate and NOR gate. So if we talk about first, we'll see the latch SR latch. So for SR latch using NAND gate, it will be like this. Okay, this is 2 NAND gate required for this. Okay, and here input will be this input. This is your S, and this is your R. Okay, and this will go to feedback to this output, and this one will go the feedback to here. Okay, so this is your Q, and this is your Q bar. And if you see truth table, so SR, we have output is what? Q. So this one is your 0 0 0 1 1 0 and 1 1. So in 0 0 case, it will be invalid state. Okay, it will be invalid state. Then for 0 1, it will be 1, means it will set. Okay, and for 1 0, it will be 0, that is your reset. And for 1 1 case, it will be no change or last state or hold state. You can say this thing when it will be 1. Similarly, we can design using NOR gate also. So NOR gate is like this. This is NOR gate. Okay, same it will be here S, and input is R, and feedback path will be go like this, and here also this feedback will go like this, but here it will be Q bar, and this will be your Q. Now here S and R, if you see the diagram, means truth table, output is what? Output is equal to Q. So 0 0 0 1 1 0 and 1. So 0 0 means hold. Here 0 0 means hold or no change or last state. Okay, using NOR gate. And when it is 0 1, then it will be reset. Okay, this is high, means it will be reset, means 0. Okay, reset. And when 1 0, then it will be set. So it is your set. And when both are 1, then it will be invalid. Okay, invalid state. Okay, this is the diagram and truth table for SR latch. All right. Now we'll talk about flip flop. Flip flop is what? Flip flop is what? If we add flip flop is a asynchronous sequential circuit. So flip flop, as we know, in latch there is no clock, but in a flip flop, if we add clock in latch, okay, if we add clock in latches, then it is called what? Flip flop. Okay, and same it will store 1 bit of data or information. Okay, now here, like if you see the difference, okay, latches and flip-flop. Okay, if we talk about some difference, if we see about latches and flip-flop, first we will see what kind of triggering they are using. So triggering, they will use trigger type. It uses label trigger. Okay, it uses label trigger, and it uses edge trigger. Okay, and apart from that, simplicity, if we talk about simplicity, then for latches is simple because it not uses clock, so we can design easily, but flip flop little more complex. Okay, now control signal, if we see control signal, then for control signal, it latches have enable line to control it, and flip flop using clock. Okay, clock signal it is using for to control application. If you see some application here, then latches both are memory element, it will store temporary. Okay, and this is for synchronous system, synchronous system. Okay, synchronous type, any kind of device is there, for that we are using this one. Okay, now same as a latch, here it has also four type. Okay, here also it has four type: SR latch, SR flip flop, then JK flip flop, then D flip flop, and T flip flop. Okay, we have four kind of flip flop. First we will see SR flip flop. SR flip flop. SR means what? Set and reset. So if you see the block diagram of SR flip flop, your block diagram will be like this. It will be S and R. This is S, this is R, and output will be your Q and Q bar. It uses one clock signal, so this is your clock. This is what SR flip flop. This is a block diagram of SR flip. Now if you design circuit diagram, so same, first you need to make latch. Okay, so we can design with NAND and NOR also. We are now we are designing with NOR gate. So in latch we are doing like this. Okay, here it will be like this, and here it will be, this is the feedback. Like this we have designed SR latch. So in SR latch we just need to put one clock signal. Okay, one clock we need to put here. So this will become flip flop. Okay, so this is what, this is your clock. This is your clock signal. This is S, this is R. So this is the diagram for SR flip flop. Okay, now we'll see truth table. Truth table will be your SR as an input, and output is your Q. So same 0 0 0 1 1 0 and 1 1. So same as a latch, it will be no change or last state or hold state, and 0 1 it means what? Reset. Okay, a reset, and 1 0 means set. Okay, 1 0 means set, and 1 1 means what? Invalid. Invalid. Okay, in 1 1 it will come invalid. Okay, so here to you need to remember one point, like when both S and R are high. High means both are 1. In that case, then output will be invalid. Okay, then output will be invalid. So to overcome this, they introduces JK flip flop. Okay, they introduces JK flip flop. Now we'll design JK flip flop. So JK flip flop, we'll talk about JK flip flop. Now for JK flip flop, if you see the block diagram, your block diagram will be like this. This is your J, this is your K, this is your Q, and this is your Q bar. Okay, and we need one clock. So this is your clock signal. All right. Now if you see the diagram, so you need to make for first what? SR. We'll design SR flip-flop first. So as we are designing like this one, and this we have feedback tool here, and this will go here. This is your Q, and this is your Q bar. Okay. Now we have one clock signal, that is your AND gate like this. Okay. This is what? This is your clock signal. Here we are giving clock, and this is what? This is J and this is K. J and K. This is same as a SR flip-flop design. Here what changes is there? This one more input is there. It will go to feedback to this Q. Okay. And for one input here, it will go to feedback to Q bar. This is the this is the changes in SR flip-flop. So they have developed JK flip-flop. So they will get the overcome with 1 1 condition. Now you can see the truth table. So truth table is when 0 0 0 1 1 0 1 1. So in that case, when both are 0, then it will be last state, that is your Qn, or hold state. Then 0 1 0 1 means it is 0, means what? Reset. And 1 0 means it will be set. Okay. And 1 1 1 1 case it was invalid before, but now it will give Qn bar, last state bar. Means whatever last state is there, they will provide uh, complement of that. Suppose here it is in last state it is 1, then it will give 0. If it is 0, then it will give 1. Okay, like this things will be there. So what happened when this thing happened? So when both inputs is high, okay, when both input is high, so in that case it is giving Qn bar, last state bar. So it will go in a toggle mode. Okay, it will go in a toggle mode. Means it will go 1 0 1 0 1 0 toggling. It will toggling in 1 0 1 0 1 0 1 0 like this. It is toggling. So it is called race condition. Okay, race condition. It is called race condition. When it will go the toggling mode, then it will go in a race condition. Okay, just remember this type of question they will ask in which flip-flop race condition arises. So you need to write JK flip-flop. So to overcome to race condition, they introduces master slave flip flop. Okay, master slave JK flip flop. They have introduced as master slave JK flip flop. Okay, they will ask question like that also. To overcome race condition, which flip flop is used? So you need to give answer master slave JK flip flop. Okay. So we'll discuss about JK flip flop later. First we will complete our type. So another type is what? D flip flop. D flip flop is what? D flip flop is nothing but a delay flip flop. So it has only one input, that is your D, and one clock signal, and it has two output, that is Q and Q bar. Now if you see the diagram, its diagram will be go like this. Same. This is the diagram of D flip flop. It will go here and this will go here. This is your Q, this is your Q bar. Now we have clock signal, that is like this. We are designing clock signal. Okay, this is what? This is we are giving clock. Okay, and here we need to give one not gate. Okay, this is D. So here it will go D bar, and this side it will go D. Okay, so one it will go D input and one it will go D bar input. All right. So in that case, truth table will be like this. So whenever it is 0, it will give delay and it will go 0. After some delay, it will appear same output. So it is 1. So it will be 1. Now if we talk about T flip flop, okay, T flip flop. So T flip flop is same like D flip flop, only it has two input. One is T and another one is your clock signal. And here we have Q and this one is Q bar. Same diagram you need to use like this. It will go. This is OR gate. This is OR gate and sorry NOR gate. So and here we have one feedback like this. It will go and this will go like this. And here we need to make your clock signal. Okay, using AND gate. So this is your clock signal. All right, and here we have one input, that is T. So here both side it will go T only. Okay, it will go T, and we have one feedback path here. Okay, here also we have one feedback path. So it will be your Q, it will be your Q bar. This is a diagram for T flip flop. T flip flop means what? Toggle flip flop. Toggle flip flop means when it will be 0, it will toggle to 1. When it will be 1, then 0. So it will be in a toggle mode. 1 0 1 0 1 0 like this. It will be in a toggle mode. Okay. Now we have some characteristic equation of flip flop. So if you see the characteristic equation, sometime in an exam they will ask characteristic equation for a different flip flop. So you need to remember these equation. So for SR flip flop, your characteristic equation will be Sn plus 1 is equal to S plus R bar Qn. This is the SR characteristic equation. Now for JK it will be Qn plus 1 is equal to J Qn bar plus K bar Qn. Okay. Now for D flip flop it will be Qn plus 1 is equal to D only. Okay. And now for T flip flop this will be Qn plus 1 is equal to T Qn bar plus T bar Qn. This is the characteristic equation. You just need to remember all these things. Now here you need to write some more important point like about JK flip flop. JK flip flop is a universal flip flop. Universal flip flop. Okay, we can design any kind of flip flop using JK flip flop. That's why it is universal flip flop. Okay, and in JK race around condition arrive or occur. Okay, just remember this thing, and to overcome this, it uses master slave JK flip flop. Okay, just remember this all point. Now if we see the master slave JK flip flop, so master JK flip flop is what we have. It uses two JK flip flop. Okay, it uses two. This is J, this is K, and this one is your Q, and this one is your Q bar, and another JK it will use. Okay, this is your J, and this one is your K. This is your Q, and this one is your Q bar. Okay, and it uses clock signal. So this is your clock signal. Okay, this is your clock signal. Same clock will go here also with NOT gate. Okay, so that one will operate at a time. All right, and in JK we know we have feedback path, so it will go like this to here, and this will go like this to here. Okay, all right, this is your Q and this is your Q1. This is the design of JK flip flop. This will call master, and this flip flop is called slave flip flop. Okay, now here you can see this is your NOT gate. So now if clock signal of a master flip flop is 0, then it will be, suppose it will be 0, then slave will be 1. So therefore no race around condition will be appear in both 1 1 case. Okay, that's why they have used this master slave, 2 JK flip flop and 1 JK flop. This master flip flop will control this slave flip flop. Okay. Now, okay, this is about your JK flip flop. All right. Now we'll start with another topic, that is your counter. Okay, counter is also a sequential circuit. Counter is a sequential circuit that count and store it. The purpose of a counter is to it count and store the number of input pulses or events typically related to a clock signal. Okay, basically counter we have two types. Okay, basically we have two type of counter. Two types of counter we have. Okay, basically we have two types of counter. That is your first one is your synchronous counter, and the second one is your asynchronous counter. Okay, synchronous and asynchronous counter. All right. So in synchronous, what happened? In synchronous, all flip flops, are triggered by a single clock by a single clock signal. Okay, by a single clock signal simultaneously. All right, all flip flop are triggered by a single clock signal simultaneously, and asynchronous counter that we call ripple also. Asynchronous counter that we call ripple asynchronous counter. In that clock input, is applied only in one flip flop. All right, in only one flip flop, and remaining will trigger with previous flip flop. Okay, here it uses only one clock signal. Here it uses only one clock pulse or one clock signal, and that will be applied to the first flip flop, and remaining flip flop will be triggered with the previous flip flop. All right, and so this is your counter. If you see the now we'll see the diagram. So diagram will be like this. First we'll see the diagram for synchronous counter. So for synchronous counter, suppose we will design with 3 flip flop. So this will be your J and K. All right, and again this is your J and K. This is your Q and Q bar. This is your Q and Q bar, and we have one more J and K. This is your Q and Q bar. All right. So here, as I told, it uses one clock means all flip flop need a clock signal here. Okay. So here we need to put one clock here also, one clock here also. Like this, it required clock signal. As I told you in definition, all flip flop are triggered by the single clock signal simultaneously. Okay, so one clock is there, and simultaneously all clock will be applied to a all flip flop, and output we will take from here. This is your Q0, this is your Q1, this is your Q2. Like this, we are taking output. All right. Now, if we talk about asynchronous counter. So asynchronous counter is what? Asynchronous counter in that only one clock is there in first flip flop, and after that all are triggered with the previous one. That means what? That means we'll see the diagram first. then you will come to know J and K, and this will be your input. This is your output Q and Q bar. Another one is this is your J and this is K, J, K, this is Q and this is your Q bar. All right. Now here we need one clock here. Okay, this is your clock signal, and this output will appear here and it will produce clock. Okay, and here also we are taking Q0 output also. Same, this output will go here. This is your clock signal, and here we will appear output, and here will appear output. So this is the diagram for synchronous counter and asynchronous counter. All right. Now we have some other counter. We have some other counter. Some other counters we have. That first one is up counter. Okay, up counter. The first one is what? Up counter. In up counter, means we know counter, the counter function is it will count and it will store. So up counter, it will count in ascending order. Okay, it will count in ascending order. It will count the data in ascending order. Then we have down counter. Down counter. Okay, in down counter, it will count data in descending order. Okay, it will count data in descending order. Now we have up and down counter also. Up and down counter. So we have up and down counter also. The function of up and down is it can count both. It can count both. Both means it will go ascending also and descending also, means it will count both up and down. All right. And now we have module and counter. Okay, we have module and counter that will count from 0 to n minus 1 and then reset. Okay, it will count from 0 to n minus 1. After that, it will reset. Then fifth one is your ring counter. Okay, fifth one is your what? Ring counter. Ring counter will count circulate, or it will shift the register circulate. Okay, shift, or you can write count in circular. Okay, or shift register circular. All right, this is the definition. Now the last one is your Johnson counter. Okay, Johnson counter. So Johnson counter is what? It is a twisted ring counter. It is a twisted ring counter. Twisted ring counter is called Johnson counter. All right. It will complement the last state only, Johnson counter. So this is the all type of counter. And some important point you have to note down here. Some important points like that. First one for mod n counter. Okay, for mod n counter, if they ask number of flip-flop required, is to how many number of flip-flop requires to make mod n counter. So number of flip-flop is required is k. K means what? 2 to the power k is always equal to and greater than n. Okay, n is your this one mod n, and k means flip flop. K is number of flip flop. Like suppose example, if they will ask mod 10 you need to design. Okay, mod 10 counter you need to design. So mod 10 means what? 2 to the power k, it should be greater than equal to 10. So it should be greater than equal to 10. If you go 2 to the power 3, 2 to the power 3 is 8. So 2 to the power 4 is what? 2 to the power 4 is 16. That will be greater than equal to 10. So greater than equal to 10. So k is what here? K is 4. So here 4 flip flop required to design mod 10 counter. Okay. Sometime they will ask question about ring counter, that is in ring counter mod n counter, in ring counter mod n counter, for a ring counter, for to design mod n counter we required n number of flip flop. Okay, for in a ring counter, if they will ask using ring counter how many mod n counter required to, means how many flip flop required to design mod n counter. Suppose they will ask mod 3, we need to design mod 3 ring counter. Okay, mod 3 ring counter, we need to design mod 3 ring counter. So n number of flip flop, n is 3, so 3 number of flip flop required to make mod 3 ring counter. Just remember this all points. Okay, now we'll talk about shift register. Another point, another topic is your shift register. That is what? That is also a sequential circuit. So a shift register is a sequential circuit, logic circuit made of flip flop which is used to store and shift the data. Counter is what? Counter is count and store, and here it shift register, what it will do? It will shift the data and store it. Okay, data can be shifted either to the left or right. It can shift either left or either right, it can shift. Basically we can use shift register as a data storage, data transfer, data manipulation and timing operation. For this purpose we are using shift register. Okay, and basically it uses D flip flop. Okay, basically it uses D flip flop to design counter. Suppose if we see the diagram for counter, okay, we'll take 4 flip flop for D flip flop to design this one. So this is your D as an input, all right, and this is your D. This one is your output. This is your D, and this is your Q, this is your D input, and here we will get output Q. Okay, and in D flip flop we required one clock. Okay, so here we required one clock, like this it will go one clock, this is one clock, and this is one clock signal. This is what? Clock signal. All right, so we can shift the register serially or parallel. Okay, so this is what? This is serial flip flop design. Now if you, this is what? This is serial shift register. Now if you see parallel shift register, so in parallel shift register, same we'll see like this. This is what? D flip flop, we need to design D flip flop here, D, and here it will be Q, and this is D, this is Q, this is D, this is Q, D and Q. So this is your D, this is your Q, this is your D, this is your Q, this is your D, and this is your Q. Okay, now same here, you required a clock signal in every flip flop. So this is your clock, this is your clock, this is your clock signal, this is clock. Parallel means what? Parallel data will in and parallel it will go out. So this is input and this is output Q0. This is Q0, Q1, Q2, Q3. Okay, the data will go parallelly D0, D1, D2, D3. All right. and this is what Q1. So output will be like this. This is input, this is output Q3. This is, sorry, this is Q2. This is input, this is output Q3. Like this, your serial and parallel shift register is there. Just I gave you example for designing shift register. Shift register will design like this only. Okay. Now we'll see some type of shift register. Okay. We'll see some type of shift register. Type of shift registers. So basically we have four type of shift register. First one is your SISO. Okay. Basically we have four types. Basically we have four types. First one is your SISO shift register, that is your serial in, serial serial out shift register. Okay. And here data data will in serially and out serially. Okay. Data will in serially and out it will serially. Okay. And it is used for data transfer. It is used for data transfer and time delay. Okay. SISO is used for data transfer and time delay. Now we have serial SIPO. SIPO means what? Serial in parallel out. Okay. Serial in parallel out. Here data in serially and out parallelly. Okay. So it is used as a serial to parallel converter. Okay. Now the third one is PISO. PISO means what? Parallel in and serial out. So here data in parallelly, okay, and data out serially. All right. Now it is used as a parallel to serial converter. Okay. Now our fourth one is PIPO. PIPO means what? Parallel in and parallel out. Okay. Parallel in, parallel out. Here data in parallelly and data out parallelly. Okay. So it is used for temporary data storage. It is used for temporary data storage. Okay. So this is all about four type of shift register. Apart from that, we have some other type of shift register. Okay. We have other type of shift registers. Basically, we have two type of shift register, two type of other shift register. First one is your bidirectional. Bidirectional shift register. So bidirectional shift register, it can shift the data in both sides. This can shift data both sides. Both side means left and right. It can shift the data left and right, and it is used for arithmetic operation. It is used for arithmetic operation. Now the second one is universal shift register. So universal shift register, as we till now you have understand why all things are universal, like JK is universal, NAND and NOR are universal, because using this we can design any kind of we can design any shift register. Okay, register. That's why it is universal shift register. All right. So this is all about your shift register type and all. So here our sequential circuit is over. Now all sequential circuit we have discussed. Now we have another topic, that is data converter. So data converter we have generally two types. Okay, data converter we have two types. Okay, the first one is DAC. DAC means what? Digital to analog converter, and ADC. ADC is analog to digital converter. Further, DAC we have two types. First one is weighted register, and another one is R2R. R2R ladder. This two type we have DAC, that is digital to analog converter. Now for ADC we have four type. Okay, ADC we have four type. First one is your RAM type or counter type ADC. Okay, and the second one is flash type ADC, and the third one is your SAR. SAR means successive approximation register, and the last one is dual slope register. Dual slope or you can say this is integration type ADC. Okay, so we have four type of data converter, ADC. Two type of data converter we have: digital to analog, analog to digital converter. Digital to analog we have weighted register, R2R ladder, and ADC, that is analog to digital converter, we have RAM type or counter type. Then flash type ADC is there, SAR is there, and dual slope integration type ADC is there. Okay, now first we see DAC, that is weighted register DAC. If we talk about weighted register DAC, so weighted register DAC, if you see, we have register like this in weighted register. Okay, if it is R, then it will be double 2R, then 2R it will be double 4R, like this, and this is called MSB, and this is called LSB. Okay, this is called that first one is MSB bit, and this one is LSB. So DAC means what? Digital okay, digital to analog converter. So it produces analog voltage. Okay, in output it will give analog voltage. All right, and this analog voltage we are calculating is using V naught is equal to resolution into gain into N. Okay, so this resolution, this is the formula for analog voltage V naught equal to resolution into gain into N, and the resolution is what? Resolution is equal to VR reference voltage and 2N minus 1. This is the formula for the resolution. Okay, resolution, and this resolution is also called step size. Step size, and we can write this one also as a VFS. Step size is what? VFS, full scale. So we can write this one VFS divided by 2n minus 1. This is the resolution formula. Okay, and 2n minus 1 is what? Number of step. Number of step is what? 2 to the power n minus 1. Okay, sometimes they will ask for in a numerical like find LSB or RSB, MSB. So register LSB is equal to register MSB into 2 to the power n minus 1. This is the formula to calculate LSB or LSB. Okay, this is RMSB, this is RLSB. So this is the formula for weighted register digital to analog converter. Generally they will ask numerical and they will give all the value. Just you need to put the formula and get the answer. If we talk about R2R ladder, in R2R ladder your diagram will be like this. Okay, so it will be like ladder. It will be like ladder of this is R, this is 2R, this is 2R, this is R, this is 2R. Okay, and this is also 2R, and this bit is called LSB, and this bit we call MSB. All right. So here also we are finding voltage, analog voltage, because it is DAC, so it will convert in an analog form. So we will calculate analog voltage. So formula is same for here also. V naught equal to resolution into gain into N. Okay, same formula. Voltage is equal to resolution into gain into N. But here the resolution is what? Here the resolution is VR divided by 2N. Or we can say VFS divided by 2N. This is the difference only. Here resolution is VR divided by 2N. Apart from that, all are same here. Okay, so this is R2R, R2R ladder DAC. Now we'll talk about our next thing, that is your ADC. So ADC we have generally 4 type. Okay, so generally we have 4 type. That is, first one is your what? First one is your RAM type. Okay, RAM type. RAM type, or you can say counter type. Counter type. So here they will ask question to you related to conversion time. Conversion time. What is the conversion time for RAM type counter? So conversion time, that is your TC. So this is your 2 to the power n minus 1 and T clock. So this is the formula for conversion time in RAM type or counter type. All right. Now the second one is your flash type. Flash type ADC. Flash type ADC, here also you need to write conversion time, that is TC is equal to T clock. Here the in flash type conversion time is TC equal to T clock, T clock, T clock. Okay, so it is a fastest converter. Okay, it will convert fast. It is a fastest converter. Sometimes they will ask for n bit number of register, okay, number of register. For n bit how many register required? So 2 to the power n. Okay, for n bit flash type DAC EDC how many register required? So 2n. And number of comparator, number of comparator is 2 to the power n minus 1, and encoder size. So encoder size is 2 to the power n into n. Just remember this point. Now the another one is our SAR. SAR is what? Successive approximation successive approximation register. Okay, successive approximation register. So successive approximation register, in that your conversion time is Tc equal to n dot t clock. Okay, n dot t clock. Now, last one is your dual slope. Dual slope or integration. Dual slope or integration type ADC. Dual slope or integration type ADC. In this, conversion time will be 2n plus 1 and t clock. This is the formula for conversion time. It is the slowest. It is the slowest converter. Okay, it is the slowest converter, but it will give high accuracy. Okay, just remember these point about ADC. Okay, so this is all about revision class for your mm, digital electronics. Okay, like this I will bring some more classes. If you like this video, just tell in a comment this class how much it will help for your what exam and all. Means whenever you will go for any kind of exam, just watch this video. You will revise all the concept and all things about the digital electronics. Okay, I will bring more like this video in the next session. And in the next class I will upload some questions, some type of question, how they are asking in an exam, like this, like that question I am going to discuss in the next class. Okay, so till then, if you like the video, just hit like on a button, kindly share with your friends, and if you not subscribed my channel till now, just subscribe the channel and press the bell icon. Okay, so thank you very much. Bye.